Basic performance parameters of magnetic materials. Special topic on magnetic materials. Parameter 1. Magnetic permeability. Magnetic permeability is a physical quantity that characterizes the magnetic properties of a magnetic medium. It indicates that after current flows through the coil in space, or in the space of the magnetic core, the resistance to generating magnetic flux, or its ability to conduct magnetic field lines in a magnetic field. The specific formula is as above, where H represents the magnetic field intensity and B represents the magnetic induction intensity. The magnetic permeability is usually expressed in μ, that is the magnetic permeability of the medium, or absolute magnetic permeability. There are two concepts of permeability that need to be understood: initial permeability and the measurement of permeability. Let's first take a look at the initial permeability. The initial magnetic permeability refers to the magnetic permeability when the basic magnetization curve is H, gives all. Another concept, the measurement of magnetic permeability, is an indirect measurement of the inductance of the winding coil of the magnetic core sheet. Then, the magnetic permeability of the core material is calculated using a formula. The instrument for testing magnetic permeability is the inductance tester. In the formula, L represents the inductance, D is the magnetic circuit length of the magnetic core, V is the cross-sectional area of the magnetic core, micro 0 is the vacuum permeability, and N is the number of turns of the coil. The magnetic permeability of ferrites of different materials varies. The figure shows the relationship between the initial magnetic permeability and frequency. The initial magnetic permeability transitions and decreases when the frequency exceeds 1000 kHz. When designing inductors and ultra-high frequency transformers, special attention should be paid to the frequency characteristics of different core materials. Parameter 2. Curie temperature degrees centigrade. The Curie temperature is the transition temperature at which magnetic materials change from ferromagnetic to paramagnetic. At this temperature, the magnetism of magnetic materials will become very weak or disappear. There are many ways to represent it. Generally, the measurement is carried out as shown in the above figure. That is, when the magnetic permeability drops to 80% and 20% of its maximum value as the temperature rises. The point where the line connecting two points extends to the intersection with the temperature axis is the Curie temperature. It determines the upper limit temperature for the operation of magnetic devices. Parameter 3. Saturation magnetic induction Bs. Residual magnetic induction Br. Correction force H. C. Due to the irreversible magnetization of soft magnetic materials. In alternating magnetic fields, hysteresis loops are formed. As shown in the figure, Bs represents the magnetic flux density when magnetized to saturation. Br represents the remaining magnetic flux density after the magnetic field is removed from the magnetic saturation state. Hc indicates that after the magnetic field is removed from the magnetic saturation state, the magnetic core continues to be magnetized by the reverse magnetic field. The magnetic field intensity at which the magnetic flux density decreases to 0 is called coercive force. The relationship between saturated magnetic induction intensity and residual magnetic induction intensity and temperature. Both the saturation magnetic induction and the residual magnetic induction decrease with the increase of temperature. When designing transformers, inductors, and common mode inductors, 80% to 90% of the saturation magnetic induction intensity at high temperatures should be taken as the design parameters. Parameter 4. Magnetic loss. Magnetic loss refers to the phenomenon where the work done by the external environment on a magnetic material during its magnetization or demagnetization process is converted into heat. It includes three types: eddy current loss, hysteresis loss, and residual loss. During the magnetization process in a strong magnetic field, hysteresis loss and eddy current loss are the main types. When magnetized by a weak magnetic field, the residual loss of some materials accounts for a large proportion. Alternating magnetic flux generates induced electromotive force and current within the iron core, which is called eddy current. Eddy current loss refers to the situation where a guide body moves in a non-uniform magnetic field or is in a magnetic field that changes with time. The energy loss caused by the induced current within a conductor. The magnitude of eddy current loss is related to the way the magnetic field changes, the movement of the conductor, the geometric shape of the conductor, the magnetic permeability, and the electrical conductivity of the conductor, etc. during the repeated magnetization process of ferromagnetic materials under the action of an alternating magnetic field. The loss caused by the continuous friction between magnetic domains consumes energy. This kind of loss is called hysteresis loss. The magnitude of hysteresis loss is directly proportional to the area of the hysteresis loop. Soft magnetic materials have high magnetic permeability, insignificant hysteresis characteristics, low residual magnetism, narrow hysteresis loops, and low hysteresis losses. Hard magnetic materials have relatively large residual magnetism, obvious hysteresis characteristics, wide hysteresis loops, and large hysteresis losses. The relationship between core loss and temperature is shown in the figure. The lower the temperature, the smaller the core loss. Controlling the temperature at the point where the loss of the magnetic core material is minimal can enhance the power supply efficiency, as can be seen from the figure. When the frequency is increased from 1 kHz to 200 kHz, the loss increases nearly tenfold. Therefore, increasing the frequency has very high requirements for the core material. It should be noted that not all materials of magnetic cores have the least loss at 100 degrees centigrade, as shown in the figure. The magnitude of the magnetic induction intensity passing through the magnetic core is also related to the loss. The greater the magnetic induction intensity passing through, the greater the core loss, the lower the magnetic induction intensity passing through, and the smaller the core loss. That's all for today's content. If you want to learn more about electromagnetic compatibility technology, welcome to follow High&Low. Remember to like and save to keep the knowledge well stored. You're also welcome to share it with friends who need it.